So quiz number 1, this is all what we call linear momentum, all in a straight line. We'll add answers to the title. Oh, we have to have my favorite student, good old Anne. Anne's kind of weird. Sometimes she spells her last name with a double E. Sometimes she spells it with a K-E-Y. I don't know. I'm whimsical. I should throw like a silent Z or something in there just to really scare kids, right? All you're going to be using for this whole quiz is that momentum equals mass times velocity, and that change in momentum equals force times time. But I also will recognize that change in anything is final minus initial, and so often I may go to mv final minus mv initial equals force times time. I will use the fact that change in momentum and impulse are interchangeable, same thing. And I'll use the law of conservation of momentum, that momentum doesn't go anywhere. Number 1 wants me to find an impulse, so I'm going to write change in momentum equals. I can find impulse either by going force times time or by going mv final minus mv initial. You know what? I see the word stop. That's a v final. I see an initial speed or velocity. So I'm going to use mv final minus mv initial. It's going to be, and final momentum is 0. Yay. It's going to be negative 112 times 4. You're going to get negative 448. And the units for impulse, well, since it's a change in momentum, it's kilograms meters per second. 2 marks. I would give you 1 mark for the equation, half mark for the numbers, half mark for the answer, but 2 marks. I will be fussy here. There should be a negative. What's the negative saying here? It's saying it has to be in the opposite direction that the player was running initially. If the player was running north, you have to tackle him to the south. Okay. What is the magnitude of the impulse needed to change with the speed of a 10 kilogram body from 20 to 12 in a time of 5 seconds? What force is needed? Okay. Impulse is mv final minus mv initial. So it's going to be 10 times 12 minus 10 times 20. You're going to get a negative, and if you left a negative in your answer, I'm fine. I guess since I said magnitude, if you ditched the negative, I have to be fine with that as well. Do you get negative 80 or 80? So I'll take 80 kilogram meters per second, or negative 80. Oh, and also, what's the other way we can measure momentum? Not just kilogram meters per second, but Newton seconds. I'd take either. Since I used mass times velocity in my brain, I went mass times velocity. B. Force. Force. By the way, you could find this by going... Do you know the mass? Yeah. Do you know the acceleration? Well, I know v final, I know v initial, and I know time. So I do know the acceleration. And I could crunch that. Or, as a shortcut, I can recognize that force is change in momentum divided by time. It's impulse divided by time. I may as well do it that way since I've done a lot of the calculations from the previous line. It's going to be negative 80 divided by 5. And so you get 16 newtons, arguably negative 16 newtons, but I would take positive because, again, I said magnitude force. So, okay. 2 marks, 2 marks. As usual, 1 mark for the equation, half mark for the number, half mark for the answer. In number 3, I have 2 masses. I have a collision. I think this is going to be a job for conservation of momentum. So the sum of all the initial momentum equals the sum of all the final momentum. Before the collision, what's moving? Mass 1, mass 2, both or neither? I think mass 1. I'll call this mass 1. I'll call this mass 2. So I'm going to have momentum 1 initial. Wham, they collide. Thought maybe Connor would jump on in again. And afterwards, they stick together, so I'm going to have momentum both final. So I'm going to get M1 V1 initial equals, oh, is this linear? Yes. Then I can do this algebraically. If this wasn't linear, now I would start to dulp instead of writing M1 V1 initial. So here, I can go M1 plus M2 V final. The final velocity after the collision is going to be 3.2 times 1.2 divided by 3.2. I don't need to put brackets around that, Mr. Duke. 3.2 plus 1.8. Can I do this in my head? Well, we're dividing by 5. So dividing by 5 is the same as timesing by 10, and then dividing by 2. So dividing by 5 is going to be 0.6, 3.2. Good gosh, 3 times 0.6 is going to be 1.8. No, I'm off. I'm way off. I forgot to carry something because my answer in my head doesn't make sense at all. 0.768? I forgot to carry the 7. 0.768? Meters per second. By the way, oh yeah, you know what? I did say final speed because I was going to say technically this isn't the velocity because I haven't attached a direction, but I did ask for final speed. If you get that 4 out of 4, otherwise I would give you 1 mark for that. I would give you 1 mark if I saw that. I would give you 1 mark for getting the VF by itself and 1 mark for the answer. Then I would turn the page. Mr. Dewick, you didn't do one like number 4 in the homework. I think I did in the homework. I know I didn't in the lesson. How much kinetic energy was lost during the collision? During the what? During the collision. Okay. I think I'm going to break this up into collision and then energy. Collision. I'm going to have mass 1 and mass 2 moving. I have momentum 1 initial and momentum 2 initial. I could also have written the sum of all momentum initial equals the sum of all momentum final, but I know I'm going to run out of room, so I have to write small here. And they stick together. It's momentum both final. I'd like to go then M1 V1 initial, M2 V2 initial equals V final divided by M1 plus M2. I think the final velocity is going to be 4.2 times 1.6 plus 1.8 times 0.6. Both are east, so I'll let them both be positive. Divided by 4.2 plus 1.8. I have them moving off afterwards at bracket. 4.2 times 1.6 plus 1.8 times 0.6, both positive, both east, divided by both masses. Do you get a final velocity of 1.3? That's not the answer. They want to know how much kinetic energy was lost. I guess kinetic energy lost is going to be how much you start with minus how much you end with. Whatever's missing is what's lost. Is that okay? Justin's going to get the headphone out of his ear before I lovingly wrap it around his neck. Justin? Thank you. So, boy, people on YouTube must just think I'm a horribly violent teacher. KE lost is going to be, now it looks like initial is going to be, well, how do I calculate kinetic energy? So it's going to be a half mass 1, 4.2, 1.6 squared, plus a half mass 2, 0.6 squared. That's how much I'm starting with initially. Minus How much kinetic energy do I have at the end? A half both masses V final squared. This is pretty yucky. I may break this up into chunks. I get 0.5 times 4.2 times 1.6 squared plus 0.5 times 1.8 times 0.6 squared. So to start out, it looks like I have 5.7 joules of kinetic energy. Afterwards, I have 0.5 times 4.2 plus 1.8 times 1.3 squared. Afterwards, I have 5.07 joules of kinetic energy. Do you lose 0.63 joules? Is that right? Okay. Now, I haven't done one specifically like that with you, but I would also argue didn't really do anything new there. I combined what I know of energy. Specifically, by the way, I didn't do the law of conservation of energy here. This isn't violating the law of conservation of energy. It means you lost some kinetic energy. Where did it go? Probably sound and heat during the collision. Probably. Or maybe if this was a really heavy collision, maybe the objects deformed a little bit in the collision, because when you deform, that's a force times the distance. That's work. That bleeds off energy. So if you got that, 4 out of 4. Otherwise, I would probably give you 1 mark if I saw that. I would give you 1 mark if I saw the 1.3. I would probably give you 1 whole mark if I saw that you had clued in that to find the energy lost, it's what you kinetic energy lost. It's what you started with minus what you ended with. And then 1 mark for the answer. To be honest, it should be worth more than 4 marks, but I didn't want to hammer you on a quiz. This is one of the ones that I meant when I said so easy that it's tough. There's probably other ways you could have got there as well, but here I just was careful, but everything's linear. Oh, let's supposing, Julie, in this collision, instead of sticking together, what if it had been a head-on collision and they bounced apart? I would have negative and positive velocities here. Would I need to have negative and positive speeds on the energy side? Why not? You're shaking your head. Why not? Scalar. So I would ignore east and west for the kinetic energy portion. This is why, by the way, I think I told you this, because energy is a scalar, this is why those Formula One race cars are designed to almost shatter completely, because all of the energy, all the pieces that leave take some kinetic energy with them. It doesn't matter whether they're taking the energy going forwards or backwards or up or down. Energy is a scalar. Momentum is a different kettle of fish. Number 5 is the other question that I meant when I said it's so easy that it's tough. A says, find the impulse. Well, it's going to be mv final minus mv initial. I notice I see east and I see west. I'll let east be positive and west be negative. You could have let west be positive and east be negative. It just means if I get a positive answer, what direction will I write? East. If I get a negative answer, what direction will I write? West. I won't say negative west, though. Mass 3.5. Final velocity negative 0.8 minus mass 3.5, initial velocity positive 1. I get negative 6.3 kilogram meters per second, which I would take, or 6.3 kilogram meters per second west, which I would also take. Is that right? Yes? B says, what impulse did cart B undergo? Well, you could just say to yourself, self. It'll be the same magnitude, because whatever momentum that car A lost, car B gained. What direction would I say there, though? East. That's what I meant by that question was so easy that it's tough. Sarah, question, or am I wrong? Am I wrong, folks? Okay, so when I said, did you get that? People said yes. Okay. Is it 6.3 or am I wrong?
I think you're wrong.
Okay.
Yeah, I'm hoping you're wrong.
Oh, you know what? Hang on. I used the wrong final velocity here. It's not 0.8 west, it's 0.6 west, right?
Yeah.
Sheesh. Read the question carefully, Mr. Dewick.
Point 6.
I did 0.8 again, didn't I?
Yeah.
0.6 west, Mr. Dewick. Thank you, Sarah. Negative 5.6? Is that better?
Yeah.
So, 5.6 kilogram meters per second east. Now I'm going to pause and I'm going to say, is that right? Do we agree? Is that right? And this time you're going to give me some feedback because, okay, that works better. You guys are my error checks. I do make mistakes. Oh, what's the final velocity? By the way, you could probably do all of this by doing a collision and conservation of momentum. In other words, you could go momentum car A initial, don't write this down, momentum car B initial, wham, they collide, momentum car A final plus momentum car B final, and because it's in a nice straight line, get car B by itself. I'm going to be clever. I think I can go the change in momentum equals mv final minus mv initial. I think I can do it that way too. Just looking only at car B, which means the final velocity is going to be the change in momentum plus the initial momentum divided by the mass. Now, I let east be positive. Okay, so I have positive 5.6 plus, what was the mass of car B? 2.8. What was the initial velocity of car B? West, negative 0.8 divided by 2.8. So you could treat this by looking at both of them as a full system, or you can look at the individual mass because I know the impulse. Really what you're doing is we've kind of broken the law of conservation of energy, of momentum up, Nick, into multiple steps instead of doing it one fell swoop. Okay. 5.6 plus 2.8 times negative 0.8 divided by 2.8. Did you get 1.2? Positive or negative? What did I get here? So direction? If you did this by treating it like a collision and doing conservation momentum, the full schmear, you should have got the same answer. If you didn't, show me your work later and I'll see if you zigged somewhere. Okay. How much kinetic energy was lost? Well, kinetic energy loss is going to be initial minus final. Now, initial is going to be a half m of car 1, 3.5 v squared, plus a half m of car 2, its initial velocity squared. Now, it's west, but it's a scalar. I don't care. You'll also notice the physics actually works out that way. If I tried putting a negative 0.8 into the squared, what happens to that negative anyhow? Vanishes anyhow. So nature is telling me, dude, it's a scalar. Relax. Minus, now the final kinetic energy is going to be a half car 1. How fast was car 1 traveling after the collision? Oh, I'm looking at the wrong question. 0.6 squared plus 0.5 car 2. How fast was car 2 traveling after the collision? 1.2 squared. That should be how much kinetic energy was lost. Now, Brendan made a comment during Flex Block. He said, is this perfectly elastic? If we ended up with an answer of 0 right here, if no kinetic energy was lost, That's technically the definition of a perfectly elastic collision. It would also tell you that I've made up fake unreasonable numbers, because in real life cars are not perfectly elastic, because that collision would have had to then have been silent and no deformation and no heat. Not likely.
So it wouldn't even really be perfectly elastic in a vacuum.
Well, in a vacuum, it would help. That would take care of the silent part.
Yeah, but there would still be deformation. They're not.
Unless you had really, 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 really hard substances, or something that couldn't deform, like a proton. Okay. There's my initial, minus 0.5 times 3.5 times 0.6 squared, plus 0.5 times 2.8 times 1.2 squared. Oh, do you get 0? There you go. Tells you I made up fake numbers. I can't remember, did I? Maybe I did that one on purpose just to show you an example of a perfectly elastic collision. Now, in physics 12, we would have said technically they should have had identical masses and bounced off at 90 degrees. That's if it's a perfectly elastic oblique collision. We're not there yet. Can you give yourself a lovely score out of 22, please? Make sure your name is on them. If you need to come lawyer with me, now is the time. So last day we got much more difficult. Well, the phrase I used, I think, is we jumped into the deep end of the pool. And in fact, we left the drop off behind and started treading water. We started looking at two-dimensional momentum. And in particular, I want to look at example 4 where they didn't give me any kind of a picture.
Are we starting another lesson today as well?
We'll find out.
I hope so.
Okay. So, I think I said to you, curling is a lovely example of two-dimensional momentum, because a lot of the collisions in curling are at angles, deliberately so. But you can also see sometimes they'll do the hit and stick, where they'll do a head-on collision and the first rock comes to a dead stop and the second rock absorbs almost like all the momentum and keeps going. Those are lovely examples as well. Pool billiards is another good example of where you're having collisions at angles. So here's a curling example, but I have it hitting a bucket just so that the masses aren't identical and don't cancel, because in real life curling rocks are all the same mass. I didn't give you a picture. Okay, well, is there a collision? Yeah, this is a job for conservation of momentum. So I'll still start out by saying the sum of all the initial momentum equals the sum of all the final momentum. I'm going to use, how about an S for the curling stone, or how about a C for the curling stone, and a B for the bucket. Mass 1, mass 2, whatever works for you. Before the collision, what's moving? The curling stone, the bucket, both, or neither? Just the momentum of the stone initial? Wham! They collide. After the collision, what's moving? I think both, and I think separate. Any luck, James? Keep looking. Are there angles? 43 degrees south of east. Are there angles? Yeah. So now what do we, this is where our physics 11 and physics 12 diverge. If it was physics 11, we could go algebraic, M1V1, M2V2. Here, 4 letters, dull. Right? Do I know what the initial direction of the curling stone is at all? Okay. I don't know. What's the final direction of the curling stone after the collision? So I'm going to draw an arrow pointing east. The 3, by the way, you said 3 meters, it'd be meters per second, but I know what you mean. I'm not going to put the 3 on there. I'm going to put the momentum on here. Common mistakes, kids start putting velocities on their arrows thinking velocity is conserved. No, momentum is conserved. I think 30, yes? 3 times 10? I can do that one in my head. Plus. Ty, can you read to me the final direction of the bucket? Pause. Coming back at you, Ty. Can you read to me the final direction of the bucket after the collision? Okay, I'm going to, not to make fun of you. South of what? South of what? East. South of what? East. South of what? East. What am I going to draw first? East. What of east? How many degrees south? Which is about there. So 43 degrees goes there. How long is that arrow? Its momentum, which is going to be 18 times 2.3, mass times velocity. Well, maybe I can do that one in my head. 18 times 2 is 36. 18 times 3 is 50. So 36 plus 5.4, 41.4? Yes? You had your chance for glory. I don't care anymore. Now, in all the previous ones that were this ugly, since I gave you a picture, you could actually draw 3 little vector arrows. I only have 2. Wait a minute, though. What's between them, Liam? Sorry, what's between them? What's between the 2 vector arrows? What am I drawing a little circle around? A specific sign. How can I? Is that what you said the first time? Did you say plus or you say? Oh, I'm sorry. I thought you said what? What? Yeah. Okay. Sorry. Which means I can add them. How? So if I draw, I'm going to draw a nice big vector triangle up here. 30 and 41. I'll draw the 41 slightly longer than the 30. Really, the 30 is about 3/4 of the length, roughly. So it's going to look like this. There's the 30. There's the 41.4. And I guess, because I always go from the tail of the first to the tip of the second, this must be what the curling stone was coming in at. And this angle right here is 43 degrees. Uh-oh. That 43 is not in my triangle. Robbie, who was working on this earlier, just realized he made a mistake. And again, the reason, Robbie, not only is this, and don't kid yourself, really, really tough to wrap your brain around, there is infinite room for dumb mistakes as well. Forget the squares, forget the square roots, angles in the wrong place. Even something as simple as going 90 minus the angle or 180 minus the angle. The number of times I've done that wrong in my head. Oh, compass rose, getting east and west or north and south mixed up. Oh, and then you got to do the physics. Ugh. How can I find this angle? That was a little loud, but that's okay. How can I find that angle if I know the 43? 180 minus, because the 2 of these form a straight line. Okay? I'm going to be bold, and I'm going to go 180 minus 43 in my head. I think it's 137, but I've done that one wrong so often because you're almost always having to carry a 1 when you're doing it in your head. I will often, in fact, almost always on a test or a quiz, I'll type it into my calculator. This is one time where I humble myself and I say, I've made that mistake a zillion times. Not going to do it on a test or a quiz. Is it 137? Okay. Now, if all they had asked for was the initial momentum, I could do the cosine law and quit. That might be a nice way, Nevada, for me to give you a shorter version of this question, but still test the basic physics concepts. Or I could ask you for the initial speed, which would be find the momentum, divide by the mass, and quit. You wouldn't have to find the theta. Or I can be a total jerk and say, find the initial velocity, magnitude, and direction. Okay. If I really wanted to kick this up a notch, I could say, find the change in kinetic energy. Which would mean once you found all the speeds and all the velocities, you would then go a half mv squared for everything that was moving beforehand, a half mv squared for everything that was moving afterwards, and subtract, because change in would be final minus initial. You'd probably get a negative answer, because you'd probably lose kinetic energy in this collision. I'm pretty sure you do. Anyhow, for now, it's going to be squared equals 30 squared plus 41.4 squared minus 2 times 30 times 41.4 cos 137. $30 squared plus 41.4 squared minus 2 times 30 times 41.4 cos 137. Look for typos. Squared minus 2 times cos. Square root of that. Don't forget to square root, Mr. Dewick. And I get 66.563, which looks about right in terms of the scale of my triangle. It is a longer line, so it should be bigger than 41.4, but it's not crazily longer than 41.4. If I got like 700, I'd be nervous. So the initial momentum as a magnitude, 66.563. 5 sig figs is pretty good. What did this question want me to find? Oh, I have momentum. How do I find velocity? First of all, how do I find speed if I know the momentum? Which mass? Mass C. Oh, curling rock. Okay. So the velocity of C is going to be this divided by the mass. Was the mass 10?
It was.
Oh, I can do that in my head. So it's going to be 6.66 meters per second if I go to 3 sig figs now. That's a speed at. Now, theta would be where it's coming from. Oh. Theta would be where it's coming from. I can use this theta, unlike, remember, last day when we put our theta right there, because that was a slanty next to a slanty. That was no good to us. But this theta isn't next to a slanty, it's next to a horizontal. So this theta, north of south, east of west, what of what? It's going to be south of east. How big? Again, if you wanted to use the cosine law to find theta, you could. I'm going to use the sine law because I do have a pair now. I know both of those. So it's going to be sine of mystery angle divided by what's across from it equals sine of the angle that I know divided by what's across from it, which was 66.563. I think. Yeah. I'll times the 66.563 over to the sine theta side. In fact, you know what? I'm going to use my answer button. I actually still have this stored on my calculator, so I'm going to go answer times. Sorry, I'm going to times the 41.4 over. 41.4 times sine of 137 divided by the answer button. That's where I want to do it. Cross multiplied sloppily as well. And then shift sign of that, and I get 25.1 degrees. Connor earlier said, Mr. Dewick, what are we doing? We're going to continue on with another lesson. Oh, we have a little thought experiment. So here's the question. What would be more damaging? Driving into a massive concrete wall or driving at exactly the same speed into a head-on collision with an identical car traveling toward you at the same speed? What's more damaging? A head-on collision or driving into a brick wall? Brendan, what was that?
Where should I do this on Mythbusters? So I don't remember it.
They did some really good physics on Mythbusters. What do you think? Yeah,
Are they not the same?
convince me.
Does the impulse would be the same?
First, do you remember, I'll let you keep going in a second, but remember last day we looked at, or a couple of days ago, we looked at a collision and I said, what does the damage is not the force. What does the damage in a collision? Okay, acceleration. So really what we're asking, what you're going to argue, I think, is that the acceleration has to be the same and you can get there from impulse. Okay, so convince me. I agree with you, by the way. I think they are the same. Why?
Because if both forces come in pairs, then the concrete wall would have the same force on the car.
In fact, let's just look at the red car, okay? If the acceleration is what does the damage, yes? I think in both of these, it'll experience the same force, the same time of impact, and therefore the same acceleration, the same impulse. And Mythbusters, Brendan, got this one wrong. So Jamie Heineman, what they were doing was they wanted to simulate a car going at 100 miles per hour, and so they did it by having two cars crash head-on at 50 miles per hour each. And Jamie said, because that'll be the same as going 100 miles per hour. And he got called out on that. Many viewers wrote in, and nobody. They did the whole shoot, and nobody on the crew called him on that either, because it's not that intuitive, Nick, if you really haven't steeped yourself into the physics. Most people would say, oh, head-on collision's far worse. No.
You guys have lecture?
You didn't leave one for him? Oh, okay. Try example 1 on your own. I'm going to do it up here. Here we have a collision. I want you to find the final velocity, magnitude, and direction of object B. It's really similar to when we did last lesson, but I hope I changed the numbers. Let me just double check to make sure I did change the numbers from example 5. Yes, instead of 9.3, apparently I changed it to 8.5. And instead of 51 degrees, apparently I made it 38 degrees. There, it's a whole new question. So if you're really stuck, you can look at how we handled example 5, or you can try doing this from your knowledge of two-dimensional momentum. This would be fair game as a written question. I would consider this on your test a medium nasty written question. I think on your test, I'll probably give you one collision at angles, Julie, where there aren't right angles. We got to use sine law, cosine law. I'll probably give you one where it is lovely right angles, so you can use Pythagoras and SOHCAHTOA, which is way easier. And then I'll probably give you one where things are in a straight line, but you better believe there's going to be a change in direction. So try this on your own. I'll do it up here. Let's see if we all get to the same spot.
Assuming A is the one that goes downwards, right?
The 12.1 kilograms is the 12.1 kilograms? Yeah, you know what? I think the 12.1 kilograms is the 12.1 kilograms.
Stupid question.
No. Well, maybe. You shouldn't feel bad because it's a diagram I cobbled together and it's terrible. But so Drake's going to pick up a writing utensil and try this. Now that he's stretched and he's loosened up, he's not going to pull a muscle in writing. That's good. Always stretch before you start writing. If nothing else, hopefully Drake wrote that because it's a collision. Oh, these are yucky numbers I made up. Yeah, these are not good numbers. I drew my triangle wonky like that because I'm thinking about the scale and I'm betting that's what it's going to look like. Because 102 is really long and 15.73 has got to be really short compared to it. In fact, I'll even bet this is a lousy scale. I'll bet you it's going to be a really long, flat, skinny triangle. I'll bet you, because I made up lousy numbers. I should have made this velocity a little bigger because it's slowing down an awful lot.
Can we draw a triangle different than that?
Pardon me? You can go, it's just your answers that you find aren't going to match what your triangle looks like.
Yeah, okay, 'cause I flipped mine like that.
Oh, you flipped it? Oh, you went up, then down?
Mine looks like a classic triangle.
You went like this? Okay. That would give you the theta inside the triangle, which is convenient. Pretty sure.
The theta inside? Oh, yeah.
The theta. It wouldn't give you the 38 inside the triangle. You have to do a little bit of math to get the 38 inside the triangle.
Yeah.
You have to do the Zangles, I think. I'll since I drew this first, then that, I'll draw it that way, but you can handle both. So. Whew. So you're going to get an east of north, I think, theta when you're done, and you'll get the 90 minus whatever I get, the complement of my angle, if you want the fancy math term. Robbie, I'm a big fan of using the answer button. And I know that I wanted the 90.9715, but I preferred to have the answer button right there. So after I got that 90.97 and divided by the mass to get the velocity, I times it by the mass again to get that back in my answer button because I'm that lazy and I know actually I've counted the number of keystrokes. It is less typing and more accurate.
Where you got 90.9, I got 87.9.
Am I wrong?
I don't think so, no, I'm just wondering.
Anybody else get 90.97?
Yeah.
Yeah, okay. I'm going to guess, double check just for a typo. It's 102.85 and 15.73. And then check if you type that on your calculator. And cos 38. Don't clear your calculator. I'll come look at it in 1 second, but let me just go shift sign of this before I forget. Yeah, I figured it was going to be a really small angle. 6.1 degrees. You have to be in degrees. Oh, well, there you go.
Yeah, mine is so different than that.
You'll have, hang on. Hang on. I could be wrong, unless a bunch of other people got the same answer as me, because that's how we kind of work this thing.
Yeah, I got 6.92.
Mine's all.
Hang on, let me make sure I didn't make a typo. 15.73 times the sine of 38 is 38 degrees, yes. Divided by, I used my answer button, so I didn't round off at all. Now, I didn't use a rounded off value, and this angle is so small, 6 degrees, it may, Connor, if you used a rounded off value, it may be very, very sensitive to that, and that may move you off by a couple of degrees, which is why, other reason I don't like this question much at all. So did you use your answer button, or what did you divide by? What did you write? Did you use the 90.9715?
Yeah, mine's totally different. I divided by 53.73.
On this side?
No.
Okay. Let me pause the video and come look at people's work. So you're seeing, these are complicated, you're seeing, okay? Just curious, how many of you got that answer? Okay? We just need to practice this. So I got a bunch more to do. Oh, one more to do, Mr. Dewick? You know what? I'm not going to worry about example 2 right now. I'm going to say, can you go back to the last lesson, first of all, lesson 2? Number 1 is nice and linear. You can try that. Okay? Number 5, I know the numbering. I nuked some questions. Moving east, moving north. Nah, 6 is yucky. Moving north, moving west. 7 is fair game. No, 8 is yucky. 9 is fair game. 10 is fair game. 11 is fair game. 12 is fair game. 12 is your first, I think, non-right angle triangle on this assignment. Then in the next lesson, the one that I handed out today, these are all non-right angle triangles. These suck. These are yucky. So you have 1, 2, 3, 4, 5, 6, 7. I am not going to be throwing a whole bunch of work at you after this. This is not all due Monday. On Monday, when I see you folks, I'll start the next lesson, but I'm only going to get about halfway through and I'll press pause, I think is my plan. Okay? I know I'm throwing a lot at you.